So here's a few news articles. I thought this was very interesting. I know, like a lot of people, I didn't know anything much about transgender people, but of course, recently I've heard more about it. And I thought this was a very nice article. It's very much the same thing that people found with gay people, is that there's a bunch of people out there that don't understand this and don't know what to make of it. And their attitude changes when they actually know a person in this category. Then they discover that it's really important and it really matters. Anyway, somebody's posting an image called NetScout. All right. I want to see what that's about. Let's see. I'll opening it, see what happens. It's downloading. All right, we'll see if that is. Saw this in Noe Valley. What do you think they're doing? Okay, it says it's downloading. Let's take a look. It's nearly here. All right. Oh. NetScout field testing with some kind of weird box up on a stick. NetScout. Well, no, that's fine. I really don't know. If a student knows anything about this, it might be interesting. Let's see, NetScout. Performance management. Assures digital business services against disruption and availability. Well, that sounds pretty interesting. So they can fix your network if it's broken, I guess. Huh. Network and performance management products. Yeah, and so maybe they're monitoring some kind of wireless thing with this antenna? Yeah, probing for unsecured. It's a very good question, and I don't know. If any student finds out more, let us know. Maybe they are. It looks like they're probing for some kind of a terrible packet capture tool for enterprises. Yeah, slowly driving up and down. Yeah, I'm guessing they were trying to diagnose some kind of wireless problem. It may be, as you say, an unsecured wireless network they're looking for. It might be they're just testing the strength of signal in areas to decide if they need to put up better towers or something. I know my assistant has terrible cellular reception, so her internet is really bad, even though I gave her a hotspot. And I know that's true of a lot of parts of San Francisco are dead for cell phone internet connection. Several restaurants I used to go to were. Anyway, that's interesting stuff. Let's see. That's not that interesting. Let's see. This one I thought was pretty interesting, talking about, I think a lot of us to have the ability to keep working and to make a comfortable home and often to retreat into a nicer area of the country or something. And it is an interesting issue to consider. What about all the people that can't move and what should you do about it? It's an interesting article here. All right. Talking about how this will just increase as we move into like virtual reality and everything. The rich and privileged will be sort of turning into these cloud dwellers from science fiction that live in this utopia, and all the people that actually like grow food and are poor are just sort of neglected troglodytes with an entirely different life. And that certainly is true of America, as the difference between the rich and the poor keeps growing bigger and bigger until there's just a huge separation. So the new Trump plan is to just have herd immunity. Just let everybody get sick and it doesn't matter, because again, the rich can afford to test the people around them like they do around Trump, so the rich won't get it and the poor should just get it and die and stop complaining about it, which is very standard for dictators. And at the same time, they're showing something that has come up a few times, which is that this thing is really, really bad for you. 50% of the people that get sick have neurological problems later. The US military announced months ago that if you have ever had COVID at all, you're permanently exempt from military service because they don't think you'll ever recover. And so it really is better not to get it. It would be nice if the government would actually do something to prevent it. But, you know, as one of my friends wanted a test, and it's nearly impossible to get a test around here. Finally found one source, but it is amazing how we're not doing anything to fix it. And every time they talk Trump into doing something, within a week, he forgets and goes back to just pretending it's not there. That's his solution. is to pretend it's not there. So New York City, that had the virus really badly and then really beat it down, they're now trying to have in-person classes, and they're trying to have a lot of controls and everything so they can really have in-person K through 12 and hopefully keep the virus under control while doing it. So the whole nation will be watching carefully to see if they can succeed at that. Most places that have opened up just had to close again because they really did not have the ability to prevent it from spreading at school. So I'm really glad City College stayed shut, which I think is because our state and city government demanded it, but I'm glad of it. Several teachers like me said they probably wouldn't teach in person if they told us to. And so Zoom is hiring security engineers, remote offices all over the place. Yeah, they want you to have experience discovering and fixing vulnerabilities, knowledge of the OWASP top 10, bug bounty hunting would be good. So that is actually our students by the end of our program. A lot of them have done that. They do cyber competitions, they start doing bug bounties and such, and so they'd be eligible perhaps for this. So this one I thought was pretty amazing. To traverse soft ground, they invented this thing, which just has a giant tire like a pillow, so it can roll right over large obstacles. And apparently it distributes the weight so well it can roll right over people without hurting them and such. So, most sort of an extreme version of a dune buggy. So HackerOne is having a contest coming up, a virtual live hacking event for 4 days. It's in my calendar, so it's something that might be good to do, worth extra credit if you try it. Let's see, we got few minutes yet. There's also a study about the coronavirus showing that masks really are very effective. The amount of sickness you get from getting coronavirus is dependent on how big a dose you get. So if somebody is coughing and there are particles in the air, if you inhale less of them, you will get less sick. So the mask is really good, even though the masks are not perfect and they leak and they're not, N95 masks necessarily, they still stop some large portion of the particles that you would be breathing in and make you a whole lot less likely to get very sick. So that's very good. So Elon Musk has got this brain implant. He's demonstrated in a pig. He wants to put a chip in your brain that will augment your abilities with computer power. This is a science fiction standard forever. And the head of Google, one of the chief owners of Google, talked about a Google chip in your brain so you can connect to wireless and just have the internet all the time. I thought it sounded pretty good. I'm not going to be in a hurry to do it, I guess. I'm less excited than I used to be about it. But anyway, he's developing a technology. And so some people say this is wonderful. Other people, serious neuroscientists, which I used to work with them. I used to work in a vision research clinic, and they did brain surgery there and stuff. And they've been doing this for years for people that have a certain kinds of blindness or epilepsy or things like that. But what they found is it doesn't really help you as much as you think. And that's why this guy said it's all just theater. This is never going to work. It's not clear. But the problem is, even if the technology exists to stick a bunch of electrodes in your brain so they can see what the voltages are in the cells and pump in electricity. The problem is the pattern of electricity that means anything is kind of random and individual. So it's not clear how to read it and interpret what's going on, or to feed in data and have it properly interpreted. So, there's a huge issue there. But, maybe it'll work. Yeah, you'd rather have a tank roll over you? Yeah, I don't know. Yeah, at first I thought I'd be the first one to jump on the Google chip, but no, I'm not so sure. I think like a lot of us, a couple of decades ago, we thought the internet was just wonderful and it's going to be great. And now we kind of see that it's not really all that great and it's kind of annoying. And I'm not sure I really want more internet all the time. So anyway, Trump and also Ron Johnson and a lot of people and Republicans are saying this is great. We should have more teenagers with guns out there shooting people. They're citizen soldiers, and this is great. We will see where this goes. It is, as we watch the America descend into a dictatorship, it is more and more this craziness. And the thing, one of the classic things about a dictatorship, which I didn't know until I knew people that lived in them. My Spanish friend said it was great when the Spanish dictator was there, Marco. Franco. And so there was a group that loved Saddam Hussein. The thing that people, Trump does the same thing. Dictators are usually good for one group of people. They have some group of people, like typically an ethnic group, and they like that group, and they really take care of that group, and that group loves them, and they just oppress and abuse the other groups. And that's totally where Trump is. He's like not bothering to ship coronavirus supplies to blue states, and wants to cut off their education funds and everything, saying, well, they're not really us. We're the Republicans, and the Democrats just aren't really part of our team, which is very common dictator stuff. So anyway, this is kind of amazing. California had a lack of firefighters because they emptied the prisons by letting out a lot of people so they wouldn't get coronavirus. And a lot of our firefighters are convicts who get the privilege of fighting fires for $2 a day of pay. That's how they do a lot of the firefighting. And the problem is they sell it as a rehabilitation means, where they're learning a profession. But when they get out of prison, they are not eligible to be firefighters because they have to get an EMT certification, and you can't get it if you're an ex-felon. So this is a very disturbing policy in many ways. And they are, anyway, one thing that would make it better is they're trying to pass a law that will let these people become firefighters when they get out, at least, which would seem to be one way to go. Anyway. All right, so we're here at 126. And so what I'm planning to do today is we'll talk about assembly code, and then I'm going to demonstrate the next Ghidra. I've looked up how to pronounce it, Ghidra. All right, next Ghidra project, which lets you see the assembly code, and we'll be using a lot more of it as we go ahead. We're not going to do a lot of real coding, but we will read assembly code and manipulate it in simple ways. So here we are. And by the way, there is an assembly language course at City College. I think it's MIPS and not x86, but people tell me it's really quite good, and it really would help. It's not an official requirement to take this class, but certainly if you get involved in reverse engineering, malware analysis, or exploit development, it would be good to take a real assembler course and really learn assembler. Here we're just doing the CS270. Good, Craig knows. I've heard, my students have told me that's a good course. It helps them a lot. So definitely it's something to check out. Anyway, so what we're doing here is not as much as you learn in a whole course, just the very basics. So anyway, here's the basic techniques. There's basic static analysis, where you look at malware without looking at the code and without running it. You just do things like look at the hash value, look at the strings and things like that. Then there's basic dynamic analysis, where you just run it and see what it does to the operating system, what the network traffic is and stuff. And both, again, you don't look at the code, you just run it. But disassembly is the advanced static analysis, where you actually look at the code of compiled code and figure out how it works, which is very difficult. And there are tools to make it easier, but it never gets easy. It moves from impossible up to very hard, and that's about as easy as it gets. And we're only going to do a very simple little bit of it in this course. So in general, for your computer programming, there are different levels of abstraction. The authors of a program typically work in a high-level language like C or Java or something, and they write sentences that are a little bit like English. Then they run it through a compiler to turn it into machine code, which can be run on the machine. The hardware processor can only run machine code in this binary language, written here as hexadecimal. That's all it knows. And when you try to analyze a compiled program, if it was compiled with debugging information, then it would have enough information to get all the way back to source code, or close to it. But typically, distributed malware, and for that matter, distributed commercial products, do not have the debugging information because it just makes it bigger and it helps reverse engineers, and they don't want reverse engineers to do it. So you cannot get back to this high-level language, which would be nice. Instead, you get partway back. You get to this stuff called assembly code, which is a series of instructions, but unlike instructions here that will print a string and then a carriage return, and you can just read it right there, you move 1 byte or maybe 32 bits from one register to another. You do strange instructions that move only a few bits or bytes around at a time, and they aren't easy to understand what they're doing like it is here. So learning to read that is a very important skill in malware analysis if you're going to do the difficult stuff of advanced static analysis. So the hardware works with the binary code. There's microcode and these various other types here. So the hardware is just digital circuits. They're transistors in modern computers that do XOR, AND, or and not. These are just gates that flip bits around in a certain pattern, so you can combine two inputs to get an output. And you can gang a lot of those together to create things like addition and subtraction and XOR for bytes and such. And by the way, this is what's different in quantum computers. In quantum computers, you have different fundamental operations like entanglement and superposition, which are different than these things. And that's why quantum computers can do certain problems much faster. But anyway, we're talking about normal digital computers here, the common type we're using. There is microcode, which is what you get if you run something like Java. You get down to this partly compiled code, and this is stuff that runs in special hardware like Internet of Things devices. And that is a very interesting topic. I would like to have a course in Internet of Things and reverse engineering and car hacking, but and we have an expert. Elizabeth is an expert in those things, but we haven't got the ability to add new courses at the moment because, as you know, the college is in great turmoil. And last I heard, they were supposed to be cutting a bunch of stuff, but now they haven't. Anyway, adding new courses, I think, is going to be off the table for a couple of years here anyway. But anyway, we're not going to do this. We're going to do malware of the type that infects general purpose computers, the common type. So yeah, microcode, the same as CPU opcode. It is not. Microcode is, I've heard it used two ways. One is this, there's bytecode, is the stuff you get when you compile Java, where it compiles down to partially digested code which runs in a Java virtual machine. Microcode here is stuff that runs on a specific processor, and it's typically a 8-bit processor and a specialized processor. So I think it is essentially the same thing. It's the same thing as machine code, but for a specific machine. Anyway, what we're going to run here is the kind of machine code that runs on general purpose processors, primarily Intel x86. So you write your code in a high-level language, you compile it, and then you get machine code. And so low-level languages are languages created to try to make the machine code easier to see. So you have assembly language with these mnemonics like push and pop and move, and those are an attempt to make binary machine language more readable by humans. And of course, nobody writes assembler directly very easily, although it's kind of fun to do, but it's very difficult. It's a lot of work to move simplest thing in assembly. Most people prefer to write in high-level languages like C and C++. There are interpreted languages, by the way, like Python, where you, and you can run Perl this way too, where each line is interpreted one at a time and executed instead of making a file which is compiled, and that's fine too. But what we're talking about here primarily is compiled code, and primarily from C. All right, so reverse engineering is the task we have here. This is when you have a finished product that's distributed the way you would sell it as runnable code that is not intended to be editable. So it's not like open source code where you would have a GitHub repository with the real high-level source code so you can modify it. Things like viruses and Microsoft Word, they don't want you to modify it, so they make it difficult. So you get raw binary stuff, and all you can do is disassemble it and then try to read the assembly language. And the disassembly is not a perfect process. It is not always accurate, and it doesn't turn it all the way into code that's easy to read. IDA-Pro is the standard here, the way Photoshop is the standard for computer graphics. It is huge, expensive, hard to use. You could easily take several whole courses on how to use IDA-Pro. So we're only going to do the very simple things here. Anyway, so the assembly language is different for each processor. x86 is the most common for malware, although I suppose, like everything, it's moving to 64-bit code, but 64-bit Windows machines can run 32-bit code. So for a long time, malware was just almost always written in 32 because then it would infect both 32 and 64-bit machines. I don't know how many people are still running 32-bit machines. It may be going out of, at some point, it'll be x64 instead of x86. But I think most malware is still x86. Then there are other hardware like Sparks and PowerPC and MIPS. ARM is the most important here. ARM is used by the iPhone and by the Raspberry Pi. And a lot of people have been talking about moving to ARM. And supposedly ARM is going to be, the Mac is moving to ARM. The next version will be ARM instead of Intel. And I've been reading articles for years saying servers and desktops are probably all going to move to ARM because ARM can do more computation per unit power. But the only major platform that has really sworn they're really moving to ARM is the Mac. Anyway, so Intel x86 and really Intel x64 is the most common kind of hardware now, but ARM is coming. Anyway, all right. So the x86 architecture, the most important one, they all have this property. There's a CPU is the part of the processor that executes code. It's got registers, which are little short-term memories used to remember things while it's processing them. It has a control unit that fetches instructions and from main memory. So it fetches an instruction, it feeds it to the CPU. The CPU uses the arithmetic logic unit to flip the bits as needed. And then it puts the output wherever it's supposed to go. Perhaps it just goes right in a register. Perhaps it goes to memory. Perhaps it goes out to the hard drive. And so that, or the keyboard or the monitor and so on. So the control unit fetches it and uses the instruction pointer, which is one of the registers, which tells it the address of the next instruction to fetch. So it keeps track of where you are. We talked about the registers. They're very fast, but there aren't very many registers. So you keep on having to take data from RAM and put it in the register, calculate it, and then put it back in RAM to clean up the registers to move to the next one. Especially on x86, where there's a serious shortage of registers. x64, you have a lot more registers, and so it is less irritating. ARM, you have, again, a serious shortage of registers, so you have to take several ARM instructions to reproduce one x86 instructions. Your main memory just has a whole stack of here going from, say, 0 to 4 gigabytes or 8 gigabytes, whatever you've got. And so that's the physical memory you have. Now, your operating system allocates a region of memory to each program. It doesn't get all of it typically. And so you get a certain region of memory that's allocated to your program, and then that is broken up into sections. You put the data, the fixed data someplace, the actual machine language instructions go here. Then you have stack and heap sections. And you may have other sections too, which we'll talk about as the PE sections. Those are things that are laid out in memory. And when you do memory corruption exploits, which are the most common type, you manage to insert data which breaks the rules and leaks out of a reserved area into another area. That's how you take over machines and hack into them typically, which we're doing in the exploit development class. So the data is what you put in RAM when it loads. You can have static data that's loaded once and does not change while the program runs. You can have global data, which is accessible to any part of the program, or you can have local data that's only accessible in one function while that function is running. So the code are the machine language instructions that run the program, and the heap is memory where you're going to store something temporarily and then release it. So if you have a program that, say, takes input from the network card, then you've got some network packets coming in, you process them, you get something like an image maybe, you process the image, then you're done with the image, so you free the memory to free that buffer so it can take the next data from the network. That's the sort of thing you would put on the heap. Usually big things and things that are temporary, where you store them for a while, process them, and then you're ready to throw them away. The stack is where you have local variables used in a function that are, when you enter the function, a stack frame is created, allocating some room to store local variables. It stores them there, and those variables only exist while the program is running, and when it returns, the stack frame is discarded and the stack is available for reuse. So these are variables that only exist for a brief period of time in the operation of your program. However, old data in RAM does persist in RAM. There's a remnants problem. This is what happened to Target. Target got hacked because their payment terminals would process credit cards, and then the credit cards would remain in RAM because it didn't clear the RAM after using them. So the malware just stole them out of RAM and snuck them out of the company, which is kind of a sin and a shame. I demonstrated this at Hope years ago, stealing passwords from browsers in RAM. And it is a shame because Microsoft figured this out in 2004. Visual Studio since 2004 has had a variable type that does not have this property, that stores data and only removes it as soon as it's gone, which is what you're supposed to use for things like passwords and credit card numbers, but the developers just weren't using them. Anyway, the case of Target is the fault of the credit card processing. Yeah, that's one way to look at it. I mean, you could argue, you know, there's a variety of vulnerabilities that happened here, but in particular, that one of the weaknesses that they exploited was that the credit card numbers were persisting in RAM when they shouldn't. So that's why better written code that clears it every time it uses it would have made that attack more difficult. But there are, of course, a series of failures, and they had to greatly upgrade their security in many ways to drive those attackers out. And we're going through it in the incident response class. We're going through a textbook written by Mandiant, which is the company that saved Target. Although they have to not mention the name of the company, you can kind of tell they're talking about Target in their examples. Anyway, so assembly language instructions therefore have a mnemonic and then some operands. So this is move ECX 0x42. 0x means hexadecimal. So this number is in fact 64 plus 2, 66. And what this instruction does is it takes the number 66 and it puts it in the ECX register. And this type of notation has things backwards. You don't move the first argument to the second, you move the second argument to the first. All right, so this instruction, the move ECX, is B9 in hexadecimal. That's the pattern of bits. It takes 1 byte in x86 code to refer to this command. B9 will move a number into ECX, and then you have to put the value here. So it will look like this. All right, so it's going to be 5 bytes long. And actually, I think the zeros might be on the other side, but I'm not sure. Anyway, I have to look at it in a real disassembly to be sure. So here's the parts. You have a mnemonic, you have the destination operand and the source operand. And the move is a human, there's nowhere in the RAM is move spelled out. Move is just the word the humans see in a disassembler. All the processor sees is this stuff, B9420000. And it interprets these 5 bytes in a row as one command which it can execute. And this is Intel format, which is the more common for Windows code. AT&T has the source and destination the other way. So I'm always looking at all different kinds of code. And so what I do to avoid going out of my mind is I just look through the code for a fixed number like this. That number can only be a source. You can't move anything into 42. You can move something into memory location 42, but then it would have square brackets around it. So I find one command like this, and then I know which way it is. That's got to be the source, and that's the destination. Anyway, let's try some cahoots about this stuff, which is here, and here, and here. All right. All right, we've got 33 people, so there might be quite a few cahooters. All right. Got a place to put the winners? Good. Oh, yeah, we're up pretty high. I bet I only need to wait 10 more seconds. Okay. Okay, what part of this is the mnemonic? That's the move, the alphabetic part. All right. What language does the processor use? All right, the processor uses machine code. All these other things are just artifacts for humans to look at it. All right. What utility converts a high-level program into an executable file? It's a compiler? Good. All right. And what's the most common type of assembly language? All right, x86. Good. And where do you put a local variable? All right, goes in the stack. The heap is not local variables, they're a different kind of variable. Local variables that exist only in one function are on the stack, and we'll play with them later. All right, so it's ly, that's probably initials. If you give me a longer name, it'd be better, so my grader makes sure and gives points to the right people. Juarez is a real name, and Taurus, these look like real names. All right, okay, and I see your longer name there for ly, okay. All right, good. All right. So let's do some more of this. So then there's the issue of endianness. If you're going to store a, this is a 32-bit value, not a 64-bit value. I don't know why I thought, who wrote these things. All right, anyway, this is the 32-bit value. And if you make it big endian, it puts the most significant byte first. Oh, I see that previous example was correct. So this is the way you would normally write it. If you have 42, oh, I see. Juarez is not who I think it is. I'm glad you told me. Let me make a note of that. All right, I thought that was a real name, but it's not. All right, let me copy this and put it in my document. Good. All right. All right, good. Anyway, so this is the normal way we write numbers. If you have 42, you put all the leading zeros on the left. So this would be hundreds and thousands and so on if this was a base 10 number. But little endian, the first 8 bits are the lowest 8 bits, then the next 8 bits are here. So this is not even backwards compared to big endian, it is bizarre. You have a group of 8 bits with the most significant on the left, and then another group of 8 bits with the most significant on the left, and then another. So this is actually sort of nuts, but that is the way it's typically done, stored in a little endian way. So the stuff you see in RAM is a little hard to interpret. And network data uses big endian. So IP addresses are actually stored this way, so it can get pretty confusing if you look at the raw bytes in memory and try to tell the big end from the little end. So here's IP addresses. The local loopback address 127.0.0.1 is 7F001, and it's stored like this, not little endian, but sent over the network in big endian. So it's cruel and confusing, just like the fact that there's 2 syntaxes for assembly code, one that puts the source and destination one way and one that puts it the other way. These are the things that kind of give you a headache when you're starting out. So the operands, you can have an immediate value like 0 or 1 or 42. That's just a number that you could put in something. You can refer to registers. There's EAX, EBX, ECX, and other registers. You can refer to a memory address. You put something in square brackets, and whatever's inside there is interpreted as an address. So you could put an immediate number in there, like 400,000, and it would then go to that place in RAM, or you can put a register in there, and then it'll read what's in that register, interpret it as an address, and refer to that part of memory. And you can now read or write to that part of memory. So here's the registers you get on a 32-bit machine. You get A, B, C, and D, which are the all-purpose registers. Then you get the base pointer and the stack pointer, which point to the bottom and top of the current stack frame when you're in a function. Then you have the ESI, which is a stack index you can use, again, for general purposes, but it's used for referring to locations when you're copying strings often. There are some segment registers that we don't use much or worry about. And there's the instruction pointer over here, which is really important, that controls which instruction will be processed next. If an attacker can gain control of the instruction pointer, that's how they take over the machine. And these flags here indicate whether the last result was 0 or positive or negative, or whether there are errors, things like that. EDI, yeah, I wonder where EDI is. I think there is an EDI, and it's just not in this chart. I think there's also an EDI. I was just wondering that myself because I've used it quite a lot in my assembly code. I think they didn't put it in this chart for some reason, but it's there. By the way, a lot of them have floating point registers too, which are not here. So this list is not complete, but they're the most common ones. So anyway, those are the general registers. The segment registers track memory segments, but you usually don't have to worry about them. The status flags are what's used if you have something like jump not 0, jump equal, but you don't usually worry about the status register directly. That's just what's used to tell you whether the last instruction was 0 or resulted in something 0 or not. All right, so they're all 32 bits in size. And by the way, you can refer to smaller segments of them. This EAX has been extended twice. When I started, I used 8-bit processors, and there was one register called A, the accumulator, and it was 8 bits. That was the 6502 is when I started this back in the 80s. And then they went to 16 bits, and that was AX, I think. And then they went to 32 bits, and that was EAX. So it's extended A extended. So if you can run 16-bit code and 8-bit code in principle on this processor, and you can refer to 16 bits at a time and 8 bits at a time. So you can refer to A high and AX for a 16-bit part of the A register, and A high and A low for an 8-bit part of the A register. So you can do that. Normally you don't, because moving 8 bits at a time is inefficient compared to moving 32 bits at a time. The only place where we're doing this is if you take 127, the exploit development class, where you start writing shell code, you have to write code that doesn't have any zeros in it. And then it turns out to be very useful to refer to just 8 bits at a time. Because if you go back to this instruction we had here, way back here, here's an example of this instruction. And so this instruction to put 42 in ECX has 3 whole bytes of 0. And that is okay for normal code, but it's not okay for a memory corruption attack where you have to sneak that in a string and the null will terminate the string. So that's the main case where you would use these references to a small piece of a register, just 8 or 16 bits, chunks of a register. All right. So that's the general registers you use just to store things temporarily. And compilers are often consistent. For example, C will return the value in the EAX register by convention, and there are a few other registers, a few other conventions. All right. So there's a flag to tell you whether the last operation resulted in a 0 and whether something like an addition rolls over, and so a bit went off the end, and so on. All right, the instruction pointer contains the address of the next instruction to be executed, which means that you can only address 4 gigabytes of memory because there are only 4 billion possible combinations of 32 bits. And that's why 32-bit code is kind of on the ouch, because modern machines have more than 4 gigs of RAM. And it's inefficient to run that kind of stuff in 32-bit code. So gradually everybody's moving up to 64-bit code. All right. So can you go back to the ECX chart? Tell me this one here or this one here. So is this the one you want? Yeah. So you got A, B, C, and D, and those can be referred to in 16 and 8-bit versions. And then you got these, and I think there really should be an EDI down there. Do you have a question about it? The other one, okay. Yeah, this one here. So EAX is the way you normally use it, all 32 bits, but AX is the lower 16 bits, and AL is the lower 8 bits. Now, I've never used AH, but I guess you could. Okay, good. Let me know. All right, so move is your most common instruction, where you move data from one location to another. You use almost all the time we're using until. So this moves source to destination, and if the destination is in brackets, that's indirect addressing, where the destination is an address pointing to a location in memory. And by the way, it doesn't matter if you use lowercase or uppercase for the instruction or for the name of the register. All right. So here is move EAX, EBX. That will move EBX into EAX. That'll copy the contents of the EBX register into the EAX register. This will move 42 into the EAX register. This will move the contents of this memory address into EAX. And all these move 32 bits at a time. Unless you were to specify AL or something, it'll do a 32-bit move. This will go to EBX, interpret that as an address, go to that location in memory, and copy those 4 bytes into EAX. And here's how you often see it when you're copying a string. You have EBX plus ESI times 4. And the stack index counts the words as you move them, the 32-bit words. So you have some kind of loop where you do it, then you decrement ESI, and if it's not 0, you go back and do it again. This is how you copy a large block of memory from one location to another. You see this construction very often. And that's why there's an ESI and an EDI for a source address and a destination address. That's how it's commonly used in loops. All right. Load effective address lets you calculate addresses. So I can take the address EBX plus 8 and put it in EAX. It's a rather strange process, but this is how you refer to the address. This is how you do calculations on addresses and not on the values. Then there's compare. This should be compare. My goodness, mistakes in these slides. That's compare. And what it will do is tell you if those values are equal. So let's compare EAX to EBX there. We'll give you 0 if the 2 values are equal. There. I don't know how I left this wrong so long, but anyway. All right. That's what compare does. You can compare 2 things and see if they're equal. And then you'll have if they're equal, you'll get a 0 result. So now you can do a jump 0 or a jump not 0 to deal with the results. So here is EAX containing 0, EBX containing an address starting with B3. So if you refer to EBX directly, it would be this value. But if you put brackets around it, it would be that value. And if you put brackets EBX plus 8, then it'll be this value down here. And that's how you commonly are referring to things, for example, on the stack. All right. So you can add and subtract, increment, decrement, multiply and divide. You know, you've got all the mathematical operations, and you've got the operation that does nothing, NOP. This might seem pointless, but it turns out to be extremely useful, just like 0 is in mathematics. The original point of NOP was to pad things. There are certain instructions. Notice how instructions are different lengths. That one instruction I gave you, the move, was 5 bytes long. There are certain instructions that have to start on a word boundary. So you might have a 5-byte instruction, and then the next one has to start on byte 8 to hit a word boundary. So you need to pad in between, and that's what NOP is for. It does nothing. And in hex, it's 0x90. Attackers commonly use it for a NOP sled. When you're doing a memory corruption attack, you're injecting a bunch of code, and then you're trying to change the EIP to run the code you injected. And you often have to guess where your code is. And so to make it your exploit more reliable, you'll put in something like 1,000 NOPs. Yeah, the padding, let me just draw it here, this will do. So if I have A9, 42, 000000, that is the instruction from before. This moves into, I think, ECX. This is a 5-bit value. And if I put block spaces on the 32-bit words here, I've now got things there. Now I want to put another instruction here, and I cannot put it at this location because it has to be on a word boundary. Oh, that's just the design of the microprocessor. The design of the microprocessor does require certain instructions to be on a boundary. And this turns out to be an even bigger issue in ARM. In ARM, the instructions are all exactly the same length to avoid this problem. So since they've designed it to have the rules that certain instructions have to be over here, something down here, then you have to pad to fill in gaps. So then what you would do is you would fill this stuff with NOPs. And then you'd be able to do no harm. It will just go through here quickly. Yeah, that's all. It is, and the reason why it has to be on a boundary would have to do with the actual layout of the silicon on the chips. And if you get a layout of the physical diagram of the processor, you'll see it's really going through transistors that are flipping the bits one by one, and it turns out to be more efficient to have certain limitations. ARM does not have a NOP, but it does. That's another reason why maybe you don't even need a NOP. You can just have instructions that do nothing. Like there is an ARM instruction that moves a register to a register. So it does nothing, but technically it's not a NOP. And that's something you do in malware exploit development too. There are a bunch of things that do something very trivial that probably won't hurt your program that you could do over and over that you could use instead of NOP. But typically attackers do use NOP sleds in their attacks by tradition. So anyway, so if you see a program with like 10,000 NOPs in it in a row, that's malware. That's not something a normal programmer would do. It's something an attacker would do to increase the chance of finding the code you've injected. So the stack is where you put in the memory used for local variables, and it also has the address in the stack that it uses to return when their function is done running. And that's how buffer overflow attacks work. You have data stored in the stack, and you have addresses stored in the stack that will eventually be put into EIP. So if you're able to overrun a buffer, you can affect the EIP. And padding helps malware because it gives you a bigger target to shoot at. The most extreme example is the heap spray. Modern versions of Windows have address-based layout randomization. So every time it launches a program, it randomly moves it in all of your memory. So you don't know where you are at all. This was a problem for attackers until they found this. You could take JavaScript in Internet Explorer, and you could just define a string that included executable code, and you could then make 10,000 copies of it until you fill all of memory with copies of your string. Now you make a string that includes, say, 10,000 NOPs, and then the egg, the code you want to run. You just fill all of memory with it, and now you jump randomly to a random memory address. You have a very high chance of hitting one of those NOPs, and then it will do NOP, 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 and run your egg. So that's why padding helps. It makes your malware more likely to succeed for most common memory corruption attacks. Anyway, so you've got ESP is the top of the current stack frame, and EBP is the bottom of the stack frame. Push adds data on the stack, and pop takes data off the stack. So, all right. So you enter a function here with call or enter, you leave with leave or return. And so you've got small programs that do one thing and return, like printf. At the start of the program, there's a prologue, which reserves some space on the stack for the stack frame. And at the end, there's an epilogue that restores the stack, returning it back to be reused. And then it puts the base pointer and the instruction pointer back to the values that were stored when you went in. And I'll show you this a little later. All right, so here's what stack frames look like. You launch first you're running Windows up here, then you launch your program and it launches main, then it calls a subroutine, and that might call a subroutine, so you have a frame and a frame as you go in here. And then when you're done with this subroutine, you return here and then you return here. That's the layout of memory. All right, and inside each stack frame, you have a series of local variables. And then at the end of it, near the EBP, the end of your frame, you have the old EBP of the calling routine for its stack frame. And then you have the return address, which is the address of the instruction to resume at in the calling routine. And that's how a buffer overflow attack works. If you can overrun one of these variables, you can change this return address. And then when it tries to return from the subroutine, it returns to the wrong address. So that's how you control the machine. And now you just have to somehow point that address to an instruction you want to execute, and you can now do things that the developer did not want you to do. All right, so test is a way to compare two values, like compare, very similar ones. And here's how you branch. Jump will jump unconditionally to a new address. This will jump if the last operation resulted in 0. J and Z will jump if the operation was not 0, and there's a jump greater than 0 and jump less than 0. And that's how you do an if. And so in C, you enter the program with a main line, always looks like this. You have a main routine that can have some arguments. And so it can have a count of the arguments and then a list of arguments coming in. And those things will be stuck on the stack. So if here's a compiled C program in Linux, you copy the file foo to the file bar. So the argument count is 3. The name of the program counts. This is the 0th one, the first one, and the second one. Those are the 3 arguments on the line. Does the return instruction pop the arguments pushed to the stack? Yes, it does. That's what the prologue and epilogue does. The prologue reserves room on the stack by adjusting ESP and EBP, and the epilogue restores the old EBP, changes ESP to match the old, and then it stores the instruction pointer, so it resumes where you left off. So if there is not a memory corruption where data is somehow sent to an address it shouldn't go to, then it works fine. When you enter the function, it stores the current state, does something using different memory, and when it returns, it restores the saved values and resumes in the calling function. And you can totally watch this happen in a debugger, and we'll do that a little later. These are very good questions. Let me bring up next Cahoots, which are here. All right, let's see. Well, might be a few more coming. I'll wait a few seconds here. All right, I guess this is it. All right. Okay, what does that instruction do? Move EAX, EBX. That's it. This takes EBX as an address, goes to that location in memory, and puts whatever's there into EAX. All right, what command retrieves data from RAM? Okay, and that's the same one you saw before. All right, which one changes the size of the stack? I push, add something to the stack, and it changes the stack pointer to make the stack frame bigger. All right. Which instruction is repeated many times in buffer overflow attacks? All right, that's not good. All right, and what command retrieves data from the stack? Yeah, that's pop, the opposite of push. All right, so okay, I got WannaCry will have to tell me who they are. So will Zero. Zoe is a real name though. WannaCry, okay, good. I got WannaCry. Zero has not told me who they are, however. All right, so I'm going to stop the recording. Let's take a 10-minute break and pick up 5 after, and then I'm going to demonstrate the next Ghidra project. So I'm going to